This meeting is being recorded.
Muy buenas tardes a todos. Yo soy Daniel Duarte, editor general de Ciencia del Sur y coordinador adjunto del Festival Internacional de la Ciencia del Paraguay 2022. Hoy tendremos nuestro cuarto webinario de la serie de webinarios en homenaje a Blas Servín, quien fue uno de los mayores divulgadores científicos que ha tenido Paraguay. Esta charla se denomina Opening the Infrared Treasure Chest with the James Webb Space Telescope, que sería abriendo el cofre del tesoro infrarrojo con el telescopio espacial James Webb, y estará a cargo del doctor John Mather, astrofísico, científico de la NASA y premio Nobel de Física en 2006. Estamos muy honrados por la presencia del doctor Mather. And good afternoon, Professor Mather. I hope you are doing well today, and thank you so much for accepting this invitation.
Well, thank you. I'm very glad to be here with you.
También nos acompaña desde Encarnación el doctor Gustavo Romero, quien es director del Instituto Argentino de Radioastronomía y profesor de la Universidad Nacional de La Plata, Argentina. Este Festival Internacional de la Ciencia, que está organizado por Ciencia del Sur, con el patrocinio del Museo de Ciencias MUSI, y en Encarnación está auspiciado por la Universidad Autónoma de Encarnación. Si quieren ver el programa detallado del festival e inscribirse a las actividades que siguen esta semana, pueden visitar la página cienciasdelsur.com/festival. También queremos dar la bienvenida a todos los presentes que están allí en Encarnación. Muchísimas gracias por acompañarnos hoy. A la gente de la Universidad Autónoma de Encarnación que está patrocinando los eventos allí en Encarnación. Por primera vez estamos haciendo un evento en Encarnación y nos encanta poder también llegar a otros puntos del país. Pasando ya al tema que nos convoca hoy, el doctor Mather nos hablará sobre las posibilidades que se abrirán con el telescopio espacial James Webb, que fue lanzado recientemente y tiene al mundo expectante con las observaciones que los investigadores podrán hacer de todo el mundo. En Ciencia del Sur hemos publicado tanto entrevistas con el doctor Mather, así como artículos de divulgación sobre el telescopio James Webb, que pueden leer en cienciasdelsur.com. Esta presentación será transmitida en la página de la UNAE, en Facebook, en YouTube, y será traducida mediante subtítulos. Cuando termine su exposición, el doctor Mather, abriremos la sesión de preguntas y respuestas que va a estar traduciendo nuestra intérprete Natasha. Así que las preguntas podrán hacerlas quienes están en Encarnación con el micrófono allí en la audiencia y los que están asistiendo online mediante los comentarios de la plataforma. Así que sin más preámbulo, le doy la palabra al doctor John Mather para que pueda empezar su presentación. It's all yours now, Professor.
Okay, well, thank you very much for that kind introduction. I would like to tell everyone the story of the universe and how we're learning about it using the James Webb Space Telescope. So if you'll give me a moment, I will show you my view graphs because, of course, that's how we do things with pictures. So let me see if this works again. Do you see my charts?
Yes, yes.
Okay. So this is a project which is a joint project of the United States with Europe and Canada. And it is available to all astronomers everywhere. We'll tell you more about it later. It is a telescope which is designed especially to pick up infrared light. Infrared light is light that has somewhat longer wavelengths than the light that you can see with your eye. And it has many interesting advantages for discovering new things. I am the senior project scientist. I work at NASA's Goddard Space Flight Center, which is just outside Washington, D.C., here in the United States. And it's taken about 10,000 people to build this observatory, as well as all of the scientists and the three space agencies. What you see in the picture is a gigantic golden hexagon. That is the great mirror that collects the starlight and focuses it into the instruments. It is 6.5 meters across, and it has to be folded up to fit inside the launch vehicle, a rocket, so that we can get a telescope bigger than the rocket. It is protected from the heat of the sun, the earth, and the moon by what you see here is a large gray object. It's actually 5 thin layers of thin plastic covered with metal to keep the sunlight away and the heat away, so the telescope can be very cold, approximately 50 degrees above absolute zero. So I will show you more about why we need the infrared light in a bit. But before I do that, I want to talk about the history of the universe and the beginning of understanding. So about 2,000 years ago, ancient people already knew of the idea that solid objects and liquids were made of atoms, tiny fragments which were too small to see, but could be arranged in patterns to form the objects we do see. So this was what the poet said long ago. Everything is made of tiny things. They stick together, become things you can see and give names to. And then as time passes, they disappear. So that's a pretty remarkable insight for 2,000 years ago. Now I'll show you the more modern version. How did we get here? So we have discovered the laws of quantum mechanics almost a century ago. Now we understand that they determine the properties of everything. Solids, liquids, gases, everything else. And we have some amazing and puzzling equations to use that describe how everything that you think of as a particle actually behaves like a complex wave, using complex numbers and not just ordinary real numbers. And that everything that seems to be a wave also behaves a bit like a particle from time to time. So it's fascinating and challenging, but it seems to be true. And that's important because everything from chemistry to physics to the possibility of life is determined by the properties of the particles, which are themselves determined by quantum mechanics. So if you ask, is quantum mechanics important? Yes, of course, we are here because of it. We know that the universe is expanding, and it was very smooth and very hot when it was young. It was unstable and has been reorganized in countless different ways into complex systems with planets and stars and galaxies and rocks and clouds and biology. All of those things are spontaneous results of the expanding universe. The universe is so large and so old that things that seem to us very unlikely and even incomprehensible have nevertheless had time to occur. So as an example, we don't know how life formed, but obviously it did. Here we are. So there must have been enough time for this. We have learned since I was a child that DNA molecules in our cells are digital code that controls how our lives work. Not only is there a digital code, but of course the individual living cells have equipment, molecular equipment that can understand the code and turn it into action. So we may never quite understand that, but in truth, a human body is made out of 30 trillion cells, and each of them is a kind of digital computer. So if you're a computer specialist, you should think this is a wonderful challenge to understand 30 trillion networked computers, all of them different. At any rate, that's how we're here. And we've understood that a complex system like this can evolve over time, changing as it does of the survival of the lucky, as I call it. And when Darwin told us about evolution, people thought it was the survival of the fittest. But actually, I think we should be more humble. We should say, thank you very much, we were lucky. Engineers have learned about physics and feedback loops. And now we understand that even though you and I look like we're the same person from day to day, we are busy exchanging atoms and molecules with the rest of the world. And so most of my atoms in my body have been replaced many times, but still I am identified as John Mather. And that's a wonderful mystery as well. So now we have a story of the early universe. This is a picture that was made with my first project at NASA called the Cosmic Background Explorer Satellite. we wanted to measure the Big Bang. And this is a baby picture of the early universe. As it works out, the universe was very hot when it was young, and the heat radiation of those early times is still available to measure. It still fills the universe, and it comes to us almost equally from all directions, but not quite. So we made a map, and we found that there are hot and cold spots in the map, which we believe tell us about the conditions of the very earliest times in the universe. So it wasn't exactly smooth, it wasn't perfectly uniform, and the picture that we now have says there were random differences, some places that were just a little more dense than average. And those more dense regions were able to pull on themselves using gravity to stop their own expansion. So the Milky Way galaxy and the pieces in it were made because gravity could stop the expansion of the material in the early universe and make us. So because there are spots in this map, we are now here. Now, if you think you understand that, then you should be able to predict what happens next. But of course, that's very hard. So one of the ways that we have to do that is to build a telescope. This is a summary of the telescope. As we mentioned earlier, it's got a big golden hexagon that collects the starlight. It is the successor telescope that comes after the Hubble Space Telescope. It is more powerful. We like to say that it's 100 times more powerful than the Hubble Space Telescope. It was launched on Christmas morning last year in December, and as far as we can tell, it is still perfect. Nothing has gone wrong with the observatory, and it is meeting all of its predictions. It is just as sensitive and powerful as we hoped it would be. So we'll show you a little bit more about it in a moment. But first, I want to show you the launch. This is the launch of the rocket on Christmas morning from French Guiana on the north coast of South America. So,
and we have engine start. And liftoff. Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
So I don't know if you could hear the announcer saying, but it took only a couple of minutes before the rocket had disappeared into the sky overhead. And it was, of course, cloudy, as it usually is at the launch site. But it's a perfect place to have a launch site because it's nearly on the equator. So then, after it was in space, we had to unfold it. So this was all done by remote command. There is no astronaut anywhere near the telescope. The first thing that we do is unfold the solar panels because, of course, we need electric power to run the observatory. The second thing was to unfold the antenna that points back at Earth so that we can talk to the telescope, send and receive data very quickly. Then we begin to unfold the sunshade that protects the telescope from the sun and the Earth. Here we are unrolling covers that protect the sunshade itself from damage. This is all done, and you can see that it's extremely complicated. So how could you possibly get something so complicated to work? The answer is you have to test and test and test. We went through at least 4 rounds of tests to show that this unfolding process could work. And of course, on every time you do the test, there's something that's not quite right and you have to fix it. But after 4 times, we said we were good enough, and then we would launch it, and it turned out to be correct. Another way that we have to follow it is to make sure that there are 2 ways to do everything. So there are motors in there and other things, and every such motor has 2 sets of electrical controls, 2 sets of motor windings, and 2 sets of electronics. So that's part of how we get this to be capable of unfolding and working properly in outer space. All the same, we were all, of course, very alert and a little bit nervous to see if it would really do what we promised you that it would do. Anyway, as far as we know, it is perfect out there, and we were send it all the way out to a place called the Sun-Earth Lagrange point, L2. This was discovered in 1750 by Leonhard Euler, who had a pencil instead of a computer. Now we talk about this place as an ideal location for a telescope because it's about 1.5 million kilometers from Earth, about 1% of the distance from the sun. And the telescope orbits around this spot, and it is a place where the sun, the Earth, and the moon all appear to be in one direction, so that our one-sided sunshade, our one-sided umbrella, can protect the telescope from the heat and allow it to cool down to the very low temperature that we need. Why do we need a low temperature, by the way? We need it to be cold so the telescope does not emit infrared light itself. Otherwise, we wouldn't be able to see the most distant infrared objects in the universe. So we were actually able to focus the telescope. Those 18 individual segments on the great golden hexagon are all individual mirrors. Each one is supported on motors, so it can be adjusted to focus. So this is a demonstration that all of the instruments are in focus. We pointed the equipment at a place in the Large Magellanic Cloud, which is, as you know, a small galaxy very near to the Milky Way. And it is beautiful. It's covered with stars. And what you see mostly are stars in the picture, but in the upper right corner, you see also a picture from the mid-infrared instrument, which sees a little bit longer wavelengths. And you see that it has clouds of dust out there. So dust is a very important part of our history, locally and cosmically. So it all works beautifully. It is exactly as sharp as it was supposed to be. Here's an example showing our comparison with the telescope that we launched before. There's another infrared telescope in space called the Spitzer Space Telescope. The new telescope is about 8 times as large. So the picture is much sharper and it shows many, many, many more stars. So we're very proud of that. And you can also see the streams of dusty clouds that are out there in the Magellanic Clouds. So what are we going to look at with the Webb telescope? We are looking for everything from the beginning till now. The first object formed in the universe maybe 100 or 200 million years after the expansion began. And so we're looking for those first objects, stars, galaxies, black holes, whatever they are. It's a little bit mysterious because we've never had direct evidence of those earliest moments. Then we'll be looking at how the galaxies grow. The Milky Way galaxy, that's our home, appears to be made out of 1,000 little pieces that were pulled together by gravity over the course of billions of years. The Magellanic Clouds that, of course, you can see with your eyes because you're in the south, and I cannot because I'm in the north. Those are two similar parts to the thousands that have already been swallowed up by the Milky Way. At any rate, this is a story. We'd like to check it by looking back in time to see what galaxies were like when the universe itself was young. We will be looking at stars being born today. The picture in the lower left is called the Eagle Nebula. Stars are being born there now, and I'll show you more in a bit. And finally, we want to look for planets themselves and to try to understand something about where and when did life appear. Is it only on Earth or elsewhere? So, of course, that's a very hard problem, and we'll not be able to give you the whole answer anytime soon. So that's our 4 major scientific themes from the beginning till now. So some examples. Oh, first I want to show you for the professional astronomers, we have cameras and spectrometers. A camera just takes a picture, just ordinary, but we use much longer wavelengths of light. We cover all the wavelengths from 0.6 microns, which is red light, and you could see that with your eye, all the way out to 28 microns, which is much longer, and we certainly cannot see it. This requires special kinds of infrared detectors that have been perfected for this purpose. So we also have spectrometers that cover the entire wavelength range. A spectrometer spreads the starlight or the galaxy light out into colors, so you can see what are the materials that make up that object. We can get the chemistry of the object, we can get the temperature of the object, we can learn something about its motion, either toward or away from us, or even its internal motions from the details of spectra like that. So how good is this telescope? Well, if you were a small gray object, what we would call a bumblebee, a small insect, at the distance of the moon from the Earth, we would be able to get a picture of you if you would sit still for a long time. Both the sunlight you reflect and the heat that you emit, we would be able to detect it with the Webb telescope. We are also able to look at very bright objects. Mars and Jupiter are extremely difficult because they're extremely bright, but we did make sure we have a way to measure them as well. And finally, we are able to look at things that move in the solar system. They're bright, but they also move, which is different from all the other stars. And if we even get a new interstellar comet coming, like the one that was detected a few years ago called Oumuamua, we would be ready to point the Webb telescope at that. So here are examples of things we'll be looking at. This is the picture called the Hubble Deep Field. Astronomers decided to point the Hubble telescope at an empty place in the sky for 2 weeks. And after they had made this very long time exposure, they found thousands and thousands of galaxies and just a few stars. The thousands of galaxies were more than we expected. Then they also said, okay, astronomers, we hoped we would be able to see the formation of the most distant galaxies, the most early galaxies, but the Hubble telescope was not able to do it. Number one, it is too small. And number two, it does not see long enough infrared wavelengths to be able to pick up the light from those most distant objects. Because as the universe grows and light travels through it, the light waves also expand in wavelength. So what starts out as visible or even ultraviolet light in those early galaxies, we receive as infrared light. So the expansion rate of the universe is so high that the Hubble telescope was not able to see the first galaxies. So astronomers said, well, please build us a more powerful telescope that can see them. So we'll be looking at this very spot, but the picture will be different. We will be looking at clouds like this. This is the same Pillars of Creation location. It's called the Eagle Nebula. And on the left side, you see the visible wavelength picture as seen by Hubble. You can see that it's beautiful. It is full of clouds of dust, which are very opaque. They prevent us from seeing inside where the stars are being born today. But infrared light can go around dust grains, not just bounce off them. And that's because light is a wave, and it has a wavelength, and waves can go around objects. So the infrared capability lets us see partly inside this cloud. The Webb telescope will have much longer wavelength infrared capability, and we'll be able to see right in, see the new stars being born there. We will be looking at everything in the solar system from Mars on outwards. We will be able to look at Europa, which is a satellite of Jupiter. It has an ocean. It's covered with ice. And the ice has cracks in it, and water comes out from between the cracks. And once in a while, we can see that with the Hubble telescope. We will be watching with the Webb telescope also. And eventually, we will be sending a probe, a NASA probe, to fly through the water jets that come out to see, do they have any signs of life? Do they have molecules like hydrocarbons, complex molecules that might show that something's going on in that water underneath? We'll be also watching Titan. Titan is a satellite of Saturn, which has clouds. It has weather. It has rain and lakes. The rain and the lakes are made of hydrocarbons, hydrocarbons like methane and ethane. So it's a very interesting place. And we are sending a probe out there with its own helicopter called the Dragonfly, but not for a long time. And I think 2036 might be when it gets there. At any rate, we'll be watching it with the Webb telescope because this is another interesting spot. This is a place where nature has done an experiment for us. It has set up conditions where if life is possible using liquid hydrocarbons instead of water as a basis, then we should look there. We will be looking at planets around other stars. They're very, very hard to see, but once in a while, a planet goes in front of its star, as this sketch is showing you. and blocks some of the starlight. So when that happens, some of the starlight goes through the atmosphere of the planet, if it has an atmosphere, and comes through to our telescope, and we look for that to see if there are any signs of molecules in that atmosphere. We are hoping to see whether Earth-sized planets have a chance to have water in their atmosphere, and if those things have enough water to have an ocean on those little planets. So the ones we're looking at are orbiting around M stars, which are very small red stars, are about the size of Jupiter. So that even if we do find something out there, we'll say, well, it's not like home yet. But this is the beginning of searches for signs of life on planets around other stars. So you can participate. We have chosen 13 programs where their data will be released publicly as soon as they are taken. If you want to find more details about them, you look for JWST ERS, which is Early Release Science, and everyone will be able to get the data from the website. If you're an astronomer or you have astronomer friends that are good at this, we will be asking for new proposals to look at new objects, and they will be due in not quite a year from now. So, by the way, if you're a young person and you don't know whether your idea is good enough, we can still send it in because we do not know who you are. We have set up a proposal process called dual anonymous. That means that you don't have to be old and famous to win a proposal. And so that works. We're very proud of that. There are many ways for Spanish speakers to find original material. So here are a few. Of course, there's a Wikipedia page on JWST in Spanish. European Space Agency has made materials available in many languages. And then here I have a picture of my friend Begoña Vila, who speaks Spanish very well because she's Spanish. And so once in a while she gives public talks. You may be able to find some of her presentations online already on YouTube. So just to wrap up, there are lots of ways you can follow along with our work, and I would welcome anything I can do to help you all do that. So I think that's everything I was going to show you. Yes, so time for questions.
Perfect. Thank you so much for this presentation, Professor Mather. And now we are going to move to the questions. Pasaremos a las preguntas del público, también las personas que nos están siguiendo a través de Facebook y YouTube. Vamos a ir leyendo las preguntas que tengan para el profesor Mather. Ahí vemos algunas personas en la audiencia que están levantando sus manos.
Dani, aquí desde Encarnación ya tenemos algunos.
Adelante.
¿Se pueden levantar la mano, porfa? Le vamos a dar primero la palabra a nuestro invitado de honor también, el doctor Gustavo Romero, director del Instituto Argentino de Radioastronomía.
Thank you very much, Dr. Mather, for your excellent presentation. My question is regarding the synergies that you foresee between the James Webb Telescope and other major facilities we have here on Earth. For instance, the Atacama Large Millimeter Telescope. What can you say about that?
Yes, well, whenever anyone discovers anything exciting with a telescope, they always say, well, can I look at it with another telescope? So we have many telescopes available. We have the Atacama Large Millimeter Array, not so far from you. We have several other optical telescopes that pick up visible and infrared light up in the mountains nearby the Atacama telescopes. We have telescopes in Hawaii, and even more powerful telescopes are being built as we speak. The largest one is European. Its diameter is 39 meters. Two other international projects called the Giant Magellan Telescope and the 30-meter telescope are also under construction. So those are being built, and they have the advantage that they're much bigger. So if you can observe at the wavelengths that come through the Earth's atmosphere, then they are the perfect tool. So the Webb telescope observes at infrared wavelengths, most of which do not come through the Earth's atmosphere very well. And so they're completely complementary. So that's how partly the synergy, and it's very, very active. Every astronomer has friends that work with every other telescope. So if you see something, you will ask for your friends to give you time on another telescope.
Otra pregunta aquí. Sí, adelante. Nombre, colegio y pregunta, por favor.
Yo soy Mauricio del Colegio Girasoles, and I wanted to ask Professor Mather, what was it like working with George Smoot to win the Nobel Prize? How did the project start, and what was the experience like?
Oh my goodness. That project started when I was 28 years old. It was a very long time ago. It started at a time when the cosmic microwave background radiation had been discovered, but no one had yet measured and proved that it was really the residue of the Big Bang. And so many people wrote proposals. In fact, 3 different teams wrote proposals to NASA. My team that I organized proposed 4 separate instruments on one spacecraft to make a measurement of the spectrum to say, is this cosmic radiation really cosmic? And does it really have spots? So that ended up being the project that NASA chose to do. They added Dr. Smoot's team and another team from the Jet Propulsion Lab to my team. And then we worked together for a good long time. It took 15 years from the day of the first sketch to the launch. And then within a few weeks, we had our first scientific results, and we got a standing ovation from the scientific audience. I never understood how important it was going to be. But then we knew we had done something very, very exciting for the rest of the world. 2 years later, we showed the map of the hot and cold spots, and it was on the front page of the news everywhere around the world.
Otra pregunta.
I also wanted to ask about, he mentioned how it took many attempts to make a successful version of the James Webb. But what about other projects that didn't result? Are there any significant ones you can mention?
Yes, if you're thinking about telescopes that are coming next, there are 2 ones that are already quite well along. The next one is called Euclid. It is a small telescope about 1.2 meters diameter, built in Europe, mostly to look for the dark matter and the dark energy. And I think maybe that goes up next year. Then in about 2027, the United States is putting up a project called Nancy Grace Roman Space Telescope. It's twice as big and is also aimed at similar science, but differently. Trying to, and both of them, by the way, will observe a very large amount of the sky. So be able to find things that are very rare and very unusual. So if they see something that's unusual, they will call us up and say, we found something very strange. Can we look at it with the Webb telescope? And of course, they will also call up all their friends at all the other telescopes. Can I use your telescope too? After that, we have many great ambitions. I mentioned the 3 gigantic telescopes on the ground, and there are more coming after that.
Otra pregunta más del público. Sí, adelante.
Yes, I want to ask, how long is the telescope expected to work? As far as I know, it's impossible to make repairs or upgrades.
That's correct. We have no way to upgrade it or refuel it, but its life is limited by fuel. It needs fuel to stay in the right orbit, and when we're done with that, we're done. So we think that will last for 20 years. So was just luck, because there are other random kinds of things. Electronic parts can fail at any moment. But we have 2 of everything where we can. So I think we have good chance to live for 20 years or more.
I will want to know how far away is the telescope from Earth?
1.5 million kilometers.
Ok, otra pregunta por aquí. Bueno. Sí, aquí. Nombre, cole y la pregunta.
Hello, my name is Máximo Lopez. I'm from Girasol School. I would like to know if you have been able to understand how the dark matter and the dark energy affects in the expansion of the universe.
Yes, we do have some understanding of how they work. We don't know what they are. And so how do we know? Well, dark matter seems to have gravity. So how does gravity work? Well, it makes things orbit. The first way that we knew there is dark matter is people could see that the stars in the Milky Way and in other galaxies are going around too fast. They're going around so fast that they would fly apart if there were not more gravity coming than you can imagine coming from the stars. So we measure the mass of the galaxy, and it's much bigger than you can account for with ordinary matter. So that was the first evidence of dark matter. Then we have evidence of the dark energy coming from the rate of expansion of the universe itself. We took pictures with the Hubble Space Telescope, and the most distant supernovae, which are more or less standard kinds of objects, were about 20% fainter than they should have been. So that means they're about 10% farther away than we thought they were. And that means something's going on. The universe must be speeding up to explain that. So that's a big surprise for most astronomers. But a Nobel Prize was given for it, so now we know.
Thank you.
¿Otra pregunta del público? Sí, aquí adelante. Ok, sí, adelante, perdón.
Okay, hi, Professor. First of all, congratulations for the Nobel. And second of all, I want to know, how do you feel when you win the Nobel?
Oh, well, thank you. It's the first question was, what am I going to do with the rest of my life? Because now I'm famous. And so I have to be very careful and not to say things that I don't know anything about. And then go enjoy a big party. So as it happens, when you go to Stockholm, they have parties and speeches for 10 days. So it's the biggest science party I have ever imagined. And then come home and try to go back to doing real work.
You? Aquí. ¿En español? Sí, claro, en Spanish.
Bueno, soy Leonardo Gómez de la Fuente del Colegio Divina Esperanza y yo quería preguntarle a usted en su rol de divulgador científico, ¿qué podría decirnos acerca de esta foto del agujero negro que está en el centro de nuestra galaxia, el Sagitario A?
Okay, Natasha is translating this for me.
Voy a pedir, por favor, voy a traducir. I'm going to translate by voice. ¿Podrías hacer la pregunta de nuevo?
Que él, o sea, usted en el rol de divulgador científico, ¿qué podría decirnos acerca del agujero negro que está en el centro de nuestra Tierra?
What can you tell us about the black hole at the middle of the universe?
Oh, well, actually, not quite the middle of the universe, but every galaxy has a black hole. And that was a big surprise for astronomers. So a black hole, as you know, is a place where there's so much matter in one place that nothing can get out again because gravity is so strong. So every galaxy has one. This was a great discovery from the Hubble Space Telescope. Now we'd like to know, where did they come from? Did they come to us from the Big Bang? Were they there in the beginning? Or did the galaxies produce them? Or did the galaxies grow around them? So these are all wonderful questions and extremely difficult to answer. So black holes are everywhere. Every galaxy has them, and there are small ones as well as big ones.
Adelante.
Hola, me llamo Iván Castillo, soy del Colegio Divina Esperanza y me gustaría saber que ha estado hablando durante toda la reunión, por así decirlo, sobre los rayos infrarrojos, pero de los beneficios que tiene. Pero ¿por qué tiene estos beneficios tan especiales que lo hacen tan único? Gracias.
He wants to know about infrared light and its many benefits and why does it have such incredible benefits?
Okay, so infrared light is special for 3 reasons. Number 1, the expanding universe stretches out the light of the distant galaxies. So what starts out as visible wavelengths becomes much longer, and then that's infrared. So if you want to see the most distant universe, you have to have an infrared telescope. The second thing is that infrared light can go around dust grains that obscure our view of those beautiful places where stars are being born today. So you can see through the clouds with infrared light. And the third thing is that some things are just not warm enough to emit visible light. If the temperature of an object is below about 1,000 degrees, you can't see it with visible light, but you can pick up the infrared, the heat that it sends out. So if you want to see a planet directly, you need an infrared, or you might need an infrared telescope. So those are the 3 big reasons.
¿Una otra pregunta del público? Dani, ¿tenés preguntas de la audiencia?
Por ahora no, Edu. Estamos ahí expectantes del público en
Bueno,
Encarnación que...
Sí, acá tiene más preguntas los chicos. Adelante.
I have another question, and it's about what books you will recommend about the topic or that you read in some moment that you didn't explain this in a more simple way for anyone who is interested.
Oh my goodness. There's a really nice book by Max Tegmark recently, Tegmark. And I don't remember the title of the book, but I remember thinking that's a wonderful book. He's a really good writer.
Sí, adelante.
Bueno,
Todas las preguntas que quieran, chicos.
otra pregunta que tenía es cómo fue su trayectoria hasta poder llegar a trabajar con la NASA.
They want to know how was your trajectory from beginning until you got to work with NASA?
Oh my goodness. Well, it was a surprise. So as an elementary school student, I wanted to study electronics and astronomy. And then I learned about physics, and I wanted to know about quantum mechanics and gravity and relativity. And tried to measure the orbit of an asteroid when I was a high school student. Then when I got to college, the cosmic microwave background radiation was discovered, and the beginning of cosmology becoming an interesting subject came along, but I thought, well, that's too hard. So in graduate school, I said, I'd like to be a physicist. I want to be like Richard Feynman, the most famous particle physicist of the time. And then someone said, actually, that job is taken, and there are no jobs for that. So I found a thesis project to measure the cosmic microwave background radiation. And so I worked on that, and then we launched it. It was a balloon payload. We sent up our instrument to a very high altitude, and it did not work correctly. So I had a job offer already to work for NASA in New York City. So I thought when I got there, oh, well, I'll try something else. I'll try to become a radio astronomer. But then NASA said, we want proposals for new satellite missions. And I said, okay, boss, my thesis project failed. What if we try it in outer space? And he said, we will call up our friends. I know who to call. And we wrote a proposal, and that became the Cosmic Background Explorer satellite. And that's why I'm famous.
Una última pregunta.
Yeah.
Hello, my name is Sebastian, and I'd like to know more about the HOEE observatory. Like, I searched it a month ago. It was an article written by yourself, and
Yes.
I find it interesting because it offers a new way, like, to see the exoplanets and to understand why our universe or why our planet has met the requirements to life directly, and what would happen if we combine it with as in it is in hybrid observatory. What would happen if we combine it with infrared technology?
Yes, just a moment. I have to answer a text message here, but I'll be back in a second. Anyway, okay, I'm back. So you wanted to know about the HOEE, which is called the Hybrid Observatory for Earth-like Exoplanets. So it combines a giant telescope on the ground, ideally the biggest one, the 39-meter diameter telescope in the mountains in Chile, with a separate part in space. So the idea is to cast a shadow of a star onto the telescope on the ground, so that you can see the little planets orbiting around the star. The real problem with seeing little planets is that they're faint compared to the star. So the sun is about 10 billion times brighter than the Earth. So the only way you can see on Earth around a star out there is to block the starlight. So this is an idea. It's very difficult to do because the star shade, as we call it, will not stay in place. So we need rocket engines to push it. And it has to be 100 meters in diameter. And it has to be 170,000 kilometers away. So it's a very hard engineering challenge, but so is everything that we do at NASA. So maybe it's possible.
Hello, I'm Kiara Duan from Sunflower School, and I want to ask you more about the COBE project.
Oh, the COBE, yes. Yes, it was, this was the one I talked about earlier that came from my failed thesis project. Anyway, it was eventually was launched in 1989, and it had 3 instruments on board. One to measure the spectrum of the Big Bang radiation. And we did extremely well. We could compare it with a perfect prediction of the early universe. It's called a black body spectrum. And we got it exactly right within 50 parts per million. So the universe is anyway, that was perfect, confirms the expanding universe story. Then we made the map that I showed you, the hot and cold spots. And those hot and cold spots are very faint. The temperature of the cosmos is about 2.7 degrees above absolute zero. And those spots are 1 part in 100,000 of that. So a few micro degrees temperature variation from place to place. We had a 3rd instrument on board, and it was looking for the light of the first galaxies, which might possibly fill the universe even if you couldn't find the galaxies. So that's still a big challenge. We haven't really explained that.
Thank you.
I have one last question, Il, and if I may.
Yes, yes.
Yes, we have, well, it's a question from the audience that I received, but also I would like to know, Professor Matter, what is the selling point for pursuing a scientific career? What has been the most fulfilling part of your career, personally and professionally, and why would young people, why would you recommend young people to pursue a scientific career?
Yes, well, of course, there are two parts. One is it's a pleasure to do it. It's wonderful to discover something that's never known before. But of course, the second one is that I really have a sense that it means a lot to the rest of the world when we discover something scientific. It's a way of contributing to human knowledge that will never be lost. When you discover something that's never known before, we can keep that fact. We can build the rest of our human history on the basis of the knowledge that scientists discover. So I don't work on the part that is close to home. I don't work on how to stay healthy or to have better food or all of those things or better cars. But I work on what are, to me, really fascinating principles. And I just think it's a fascinating way to contribute to human society.
Perfect. Well, we are running out of time, so we're also letting Professor Matter go. We thank you so much for your time today and for coming online to share your experience and your work. We are definitely going to be following the James Webb Space Telescope and all the wonderful images it will certainly produce. So thank you, Professor Matter, and we wish you all the best for your work.
Well, thank you, Daniel, for the invitation. It's a pleasure to talk with you, and I wish you all the best as well. Science is so important and so exciting. Best wishes.
Thank you so much. Aplausos.
Bueno, para los que nos siguen, estamos brevemente, vamos a volver a estar con el siguiente webinario de hoy de nuestro festival sobre el libro Antología del Paraguay con los investigadores Andrew Nixon, Peter Lambert y el moderador, nuestro editor Carlos Galeano Ríos. Así que en breve estamos de vuelta y muchas gracias a todos por asistir.
Gracias.